right, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Someone's trying to get in here. All right, let's jump right into it. Okay, where were we last time? Last time. Oh my God. Okay, last time. That looks very thick. Okay, last time we looked at probability that I know today it's not working for me. I don't know if it's the magnification or what. Last time we looked at probability, sum of two dice show 10 given, or let me start writing the notation. Given one shows 6. Okay, so this bar here, remember it's read as given. Okay, and the thing is, we know. So here's the probability sum is 10 versus the probability the sum is 10 given 1 shows 6. And it looks like someone else is trying to get in here. And we looked at both of these problems before, but let me just give you another quick illustration before we get back to the point of what we were trying to say. Yeah, I think it wasn't. No, it wasn't that one. What lecture did I show you guys that in? It's been so many. Okay. No, there was one where I did the sum. Was that yesterday? Yeah, that's the guy I want. Just want you to have like a visual idea of what's going on. That went way too big. Okay. So let's look at what was going on here. In the first case, sum is 10, no restriction. We had no restriction in our sample space, has 36 possibilities, and 10 happened in 3 of them. So the probability here was 3 out of 36, okay, or 1 out of 12. Over here, we now ended up in a situation where one of them had to show a 6, which means we had to either be in this row or this row or this column, and none of these guys mattered. So these guys here, not in sample space anymore. Right? Enforcing the condition kind of reduced our sample space. So now all our total possibilities are these. And if you were to count the total possibilities, so now total possibilities, the number of total possibilities is, we can count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So now it becomes 11. And if we look at the tens, we now have 2 of them. And so now the probability here is 2 out of 11. So we saw that last time when we did that particular kind of question. Yeah, we got 2 out of 11 right there. Okay, so that's a visual representation of what was happening. When we impose a condition, in order to fill that condition, not every point in the sample space would actually make sense. And we saw this before with the 2 girls problem. Probability that if a couple has 2 children, what is the probability that they're 2 girls? That was one thing. But if I said, well, if they have 2 children and the older one is a girl, what is the probability now? And it completely changed. And the reason is, it's because all the set of possible outcomes was reduced. The set of possible outcomes was not the same. You actually changed the sample space. The idea is putting in a condition can potentially, it's actually not always, it actually doesn't always happen, potentially reduce the sample space. So probabilities may change. And we also saw the very important formula. So the formula that describes the situation was the probability of A given B. And we saw that that was the probability of A intersect B over the probability of B. In other words, here, these 2 rows that I highlighted in the table on the right, that was the set B. That is now the new sample space. And I need to choose the A that I want from that new sample space. Now notice that that new A is directly involved with the guys that were in A's before. However, this A only includes the 10s that were the intersection of the ones on the left, right? So if I pretended that in the guys on the left, I wasn't allowed to choose things where I didn't get a 6. These only 2 of those 10s would apply, right? So you're looking for the same thing, really. So there's going to be an overlap. There's going to be an intersection, but the size of the set of total possibilities where you can get those things from now change. Now this 10 here, the 10 right here, is not in play anymore because it's not in the intersection of B and the sample space and B and A. So that was the situation. And whenever you're in that situation, this is how we have it. So B here this is the condition. So it's the event that has occurred before. And then this is the event we seek given event B occurred. So given that I already have information that B happened, what is the probability that A will happen, right? So this whole thing here is that probability. This is the probability of B, probability of A given B. That's how it's read. And that was the formula. And we kind of worked through an example very carefully to see why that had to be the formula. Because when we pick things, it has to come from the intersection of A and B in order for this to work. So that was a very, very important formula. So maybe I should actually write that out, what this is. Equals the probability A will occur given that B has already occurred. Okay. So this is called, it's called a conditional probability. Which is just like a regular probability. The difference is this is a probability you're taking, assuming that you know something already happened. Like there's a condition for this to work, right? If I know this happened, what is the probability that that's going to happen, right? And so very, very important idea. It comes up all the time. Almost all probabilities are conditional because, you know, in life, you want to make a decision on something, you always have some history to go off of, right? So you're, no, given that I know this is the history, like what is the probability that this is going to happen tomorrow, right? So conditional probability is very important. And we need to know how to deal with them, and that's how we deal with them. Now, this is going to lead to some very interesting ideas in probability. So we can now talk about independent events. Yeah, now the scales up. I think I'm starting to write bigger. We can now talk about independent events. So let's talk about what those are. Suppose A, B are events that do not affect each other. That is, one occurring has no influence on the other occurring. Okay. So one happening, it doesn't matter compared to the other one. So it's like, all right, I flip a coin, and what is the probability that it will be heads or tails? And you're like, what is probably it's going to be heads, for example? You're like, probably is a half. All right, well, what if before flipping the coin, I chose a random card out of a standard deck and it's an ace? Now, if I flip the coin, what's the probability of the heads? Well, it's still a half. Like the fact that you chose an ace doesn't change the fact that the coin can only go two ways, heads or tails, right? Me having an event occur before that, that is different completely from the sample space of the other thing I want, or it doesn't affect the other thing at all, is what's called an independent event, right? That should be it. Then A and B are said to be independent events. Okay. This is what independent events mean. One happening has nothing to do with the other one happening. It's not going to affect it. The probability will be the same as if whether one happened or not, it doesn't matter. You'll measure the probability of the other guy and it'll be the same. It's not going to care. Okay. So now we have some language to talk about this and figure out some formulas. In particular, A, B independent means knowing B occurred does not have any influence on A occurring. Okay, that is the same to say that if I were to measure the probability of A given B, if B happening has nothing to do with A happening, then this probability is actually going to be just the probability of A, right? When A, B are independent, right? Because if I told you, oh, B already happened. Hey, I drew an ace from this standard deck of cards. Now, what is the probability of getting heads? It's the same as it always was. Like, what are you talking about? It's still a half, right? So the probability is not, the probability of A happening, given that B already happened, is not going to change. They have nothing to do with each other, right? But this is the probability of A intersect B over the probability of B, right? So what does that mean? Basically what this is saying is that the probability of A intersect B over B, probability of B, is actually the same as the probability of A when A and B are independent. Not in general, only when they're independent. And so this leads to the fact that the probability of A and B occurring in the case of independence is we multiply the probabilities of A and B. And this occurs if A, B are independent. Okay. So we have the following. A, B are independent. Independent. If and only if. So that's, it's not that I can't spell the word if. This is if and only if. So this just means the statement goes in both directions. If I know the left side, I automatically know the right side. And if I know the right side, it automatically means the left side. So if the following are true, if the probability of A given B is the same as the probability of A. That's one way. Another way is if the probability of B given A is just the probability of B, right? Telling me A already happened will not affect whether or not B is going to happen or how frequently. And lastly, the formula we just derived, the probability of A intersect B is going to be the product of the probabilities. So there were times in class where we were looking at probability problems and we realized that, hey, I could multiply the two probabilities, right? What is the probability that if I flip a coin twice, I get heads both times? Well, probability of getting heads on the first one is a half, and then the probability of getting heads on the second one is a half. And it turns out if you multiply a half and a half, you get a quarter. And that actually happens to be the probability. Now, do you always multiply probabilities? No, it's not true. You can't always multiply probabilities. You can only multiply probabilities when you have independence. You can only multiply probabilities to find the intersection, probability of the intersection, when you have independence. So if you're wondering in the past how sometimes the answer was the same as if we multiplied the two probabilities versus not, that didn't give us the answer, then you're going to realize that, oh, it must mean they weren't independent, right? So yeah, the probability, yeah, well, I'll just leave it at that. And we're going to do more examples, right? But again, I do want to emphasize these hold only if we have independence. Okay. So if we have independence, the probability of the intersection is just the multiplication of the probabilities, product of the probabilities. Now, there's another kind of event that students often get mixed up, but they shouldn't, because it doesn't mean the same thing. But let's look at mutually exclusive events. AKA disjoint events. So recall AB mutually exclusive means I define this as the word disjoint. AB disjoint means the intersection is empty. A and B is the empty set. Now, when two events, which are also sets, are disjoint, then we say they are mutually exclusive. And what that means, and so this means that the probability of the intersection is the same as the probability of the empty set, right? So that just means that is actually 0. So this means that the probability of A and B equals 0 if A, B are mutually exclusive. Now, a lot of students read this and say, oh, if they're disjoint, it means they don't have anything to do with each other. So it must mean they're also independent. That is not true. Mutual exclusivity and independence are completely different things. You can have any mixture of this combination. You can have things that are independent and mutually exclusive, or independent but not mutually exclusive, or mutually exclusive but not independent, or like they have nothing to do with each other, even though they might seem that way. Like when I say to you, oh, A and B, they're like separate sets, people automatically assume, oh, that must mean they have nothing to do with each other. They're independent. No, it doesn't. Right? It means the probability of the intersection is 0. Independent means the probability is the product. These are very different things. And this is one of the ways that I commonly see people's intuition getting in the way of probability. Forget your intuition. Know the rules. If you know mutual exclusive means this equation and independence means that equation, and you don't try to talk yourself into, oh, well, if they're separate, they have nothing to do with each other, then you're never going to make that mistake. But people make that mistake all the time because they don't like take probability for what it is, right? So right now I'm giving you the definitions. Independence means this. It always means this. Whenever you hear the word independence, these are what you think about. You don't think about some phrase in your head for what, oh, well, this has nothing to do with that. No, independence means these equations are true. That's what it means, okay? Mutual exclusive means this equation is true. That's what it means. It also means a few other things that we can talk about. We can also recall the probability of A or B is the probability of A plus the probability of B minus the probability of the intersection. And this means if A, B are mutually exclusive, then the probability of A intersect B equals 0. And so that would mean the probability of the union is just a sum of probabilities. So here we're in a situation where or translates to plus. The probability of A or B happening is probably of A plus the probability of B. And we saw this before when counting, actually. Whenever there was no overlap in what we're counting, the probability of this or that was we just added up the number of ways that can happen with the number of ways the second thing can happen, right? The probability will work out the same. So this leads to the fact A and B mutually exclusive. A and B are mutually exclusive. If and only if we know that these equations hold. The probability of A intersect B is 0, specifically the number 0. Or the probability of the union is the sum of the probabilities. Whenever these two equations hold, the events you're looking at are quote unquote mutually exclusive. It means that what mutually exclusive means that they cannot occur together. That's how you should think of it about it. As the phrase independence means one does not have any effect on the other, mutual exclusive means they cannot both happen at the same time. So for example, going back to my earlier example, if you look at the event of choosing an ace from a deck of cards and the event of flipping a coin and getting heads, they are independent, right? One happening has nothing to do with the other happening. If I draw an ace from a deck of cards and I flip a coin and get heads, those two events have nothing to do with each other. The flipping the coin and getting heads, the probability is a half, whether or not I drew the ace. Now, if you ask the question, are those events mutually exclusive? The answer would be no, they're not. because it's possible for both of those to happen. It's possible for me to draw an ace and then immediately flip a coin and get heads. The fact that the two could possibly occur at the same time, occur in the same experiment, means they're not mutually exclusive. So that's an example of something that's independent. They have nothing to do with each other, but at the same time, they're not mutually exclusive. They can occur at the same time. It's just that one occurring doesn't tell you anything about the other one occurring, right? So very important. Let's do an example to kind of show this. So I added two more problems to the original probability set 1, problems 9 and 10. Problem 10, I'm actually going to use it to segue into another topic. So I probably won't talk about that today. Let's look at problem 9 though. You have all 4 aces taken out of a standard deck. You shuffle them and you pick 2 of them at random. So you're shuffling the 4 aces. Let A be the event that the ace of spades and the ace of clubs are selected, and B be the event that the ace of spades is selected. Are A and B independent? And I could also add, are A and B mutually exclusive? Okay, so let's look at that. So what I'm going to do here is my, we have 4 aces. That is the ace of spades, the ace of clubs, the ace of hearts, ace of diamonds. Spades, clubs, hearts, diamonds. Okay. And what I'm doing is I'm choosing 2 cards from them. Let's say I don't care about order. So we want to get a subset of size 2 from the above. Of course, this means I am now thinking of my sample space as a set of subsets. I can get like an ace of clubs and an ace of spades, or I can get an ace of diamonds and an ace of clubs, or I can get a whole bunch of other stuff, right? Now, of course, the size of the sample space would be 4 choose 2. Right? So there would be 6 possibilities, right? So me deciding how I'm going to set up this sample space and knowing what the sample space is, I can use a counting principle to get what is the size of the sample space. I don't have to write all of them out. Once I have my visualization for how the sample space is going to work, I can actually use a counting principle to come up with the size. So I know if I were to write everything out, I would have 6 things in this set. So now let A be the event. We get, ace of spades and ace of clubs. This was given. So this implies A is actually the set ace of spades, ace of clubs. You should put the question on the other thing. Okay. And B is the event that the ace of spades is selected. So B means I get the ace of spades, but I also get someone else, maybe the ace of clubs, or I can get the ace of spades and then the ace of diamonds, or I can get the ace of spades and then the ace of hearts. Okay, so now let's check. It's very important that you realize when I say figure out whether or not the probabilities are independent, it is not good enough for you to come up with an argument in words. Well, this doesn't affect that because blah, blah, blah. Meaningless. You get zero credit for it. Proving something is independence means you have to prove one of these two equations is true. One of these three equations is true. That's the only way to do it. So, okay, let's go about it. All right, so note, the probability of A is going to be the size of A over the size of the sample space. There's one thing in A, so that's going to be 1 over 6. The probability of B is going to be the size of B over the size of the sample space. There are 3 things in B. It's 3 over 6. Now, let's say I wanted to find the also the probability of A intersect B is going to be the size of the intersection over the size of the sample space. What is the intersection, though? If I intersect these two sets, we now know about intersections. What is the intersection of these two sets?
The ace of spades, ace of clubs.
Yeah, it's literally just A, right? So that's 1 out of 6. Now, if you check, the probability of A intersect B is 1 out of 6. Is this equal to the probability of A times the probability of B? That is what you're asking. Probability of A is 1 out of 6. Probability of B is a half. So this is 1 out of 12. So you'll notice those aren't the same. Probability of A intersect B is not equal to the probability of A probability of B. Therefore, A, B are not independent. Okay, and I can say that because this equation did not work. And once that equation doesn't work, all the other 3 won't work, right? You could also find a conditional probability, right? And show that it's not, the condition actually matters. I guess I can make a few more comments as well. This makes sense since if someone told me that B occurred the chances of A occurring would change since the sample space goes from size 6 to size 3, and A is in both. So the denominator is going to change, right? So probability of A would be 1 out of 6, while the probability that A occurs, given that I'm told B already occurred, is actually 1 out of 3. If you look at that, right? If I know this occurs, that's my new sample space. A is one part, one element, one sample point of that sample space. Probability that A will occur, given that I know B is occurred, is now 1 out of 3. It's not 1 out of 6 anymore, because I know, for example, that this is not an event that has occurred anymore, right? We know that B occurred. So that's what would happen. And vice versa. Knowing A occurred affects B occurring. Right, and that's because they have, if you told me that A occurred, now there's only one thing in the sample space. Sample space is now size 1, and B is the event that an ace of spades is selected, then it's actually 1 out of 1. The probability would be 1, it would be certain. So usually the probability of B is a half, but the probability that B happens, given that I know A happens, is 1, right? So the probability of B occurring, given that A occurred, is not the same as the probability of B occurring, right? And yeah, you can just think about that for a little bit. Now, what about mutual exclusivity? Are A, B mutually exclusive? What do you think? We can reuse some of these calculations. Are they mutually exclusive? Yes, no, maybe so.
No,
Why not?
because the intersection is 1/6.
Because the intersection is 1/6. The answer here is no, because the probability of the intersection is 1/6. In particular, it's not 0. Okay. So again, yeah, you could make the argument that, A and B can't both happen at the same time, because, I mean, A and B can happen at the same time, because one of the events A is in the event B. So if I know anything in B happens, then B happened. And so that kind of means that A and B can happen at the same time. Not always. B can happen in more ways than A can happen, but they can occur at the same time. In fact, we saw that they can. The probability of the intersection is 1/6. There's a 1/6 chance that both of these will happen at the same time. And by virtue of the fact that that chance is not 0, it kind of means that they're not mutually exclusive. Now, what I would want you to do, we're going to stop there, but I want you to actually try problem 6. it's actually going to lead into a new topic, but you do know enough to actually do this from basic principles. I would say like try problem 6, do it by like it would probably be nice to do it visually, maybe with a tree diagram or whatever. A visual technique may be nice. You know, like tree diagram or table, etc. But after you do that, I'm actually going to show you a formula that could actually attack this thing. So fully go through this problem, write out everything, maybe do a tree diagram, and maybe even try to derive a formula. You can try to derive the formula. But yeah, we will stop there. So today we learned about two very, very important things that students often get mixed up, but you should not. We learned about, or we reminded ourselves what a conditional probability is, but then we learned about something called independent events. This means the events do not affect each other in the sense that one occurring has nothing to do with the other occurring, which means probability of A given B is the same as probability of A, it doesn't matter. Probability of B given A, same as probability of B, doesn't matter. It also means, coincidentally, that the probability of and becomes the multiplication of probability, and becomes multiplication. Mutually exclusive means they cannot occur at the same time. It doesn't mean one does not affect the other. It just means that they can't both happen at the same time. So that's the probability that the intersection is 0. And the probability of the union would just be the sum of the probabilities, because you'll go through 2 separate counting phases that you add together, and then you divide it by the size of the sample space. So that makes sense. And we actually did a problem where we actually went through and calculated that. And we can say, based on the equations, whether or not something is mutually exclusive. And that's how you should always do it, because otherwise it can be very confusing. And I'll give you some more examples where that it's a little bit more confusing than this one. Try this for next time. Try to get to the answer. If you can come up with a formula, great. If not, we'll actually derive a formula together that can describe this without going through a tree diagram or a table. But yeah, but you can do it both ways. The same way that in the last class we did this example by literally counting out stuff. And then I just say, oh, by the way, this formula could have gotten you to the answer also. So yeah, so you do know enough from first principles to get this answer, but we're going to get a nice formula for it next time. And without further ado, we're going to end there. Okay, that's it. Thank you for your time and attention. Hopefully that was clear. I will see you guys in the next one.